Most engineering structures are loaded with distributed rather than discrete forces. By a distributed force, we mean one that varies continuously throughout or along a structure. In contrast, a discrete load, also called a concentrated load, acts at a point. Up until now, we've treated weight as a discrete load, but mass is a distributed quantity, and weight is actually the sum of all the incremental weight contributions throughout a body. We could write the weight either as the total mass times gravity, knowing where the effective center is, or we could write it as the sum of these incremental contributions, the integral over the volume, rho, which is mass density. So this is rho, mass density, and it will generally be a function of spatial position. We could write this as the integral of mass density times g over the volume. As this figure suggests, the lift an airplane wing experiences is the result of differential pressure between its lower, higher pressure, and upper, lower pressure surfaces. If we had to make every engineering decision by tracking every detail of a distributed force, it would make our jobs quite tedious. Fortunately, there is a process for taking complicated force distributions and reducing them to their simplest possible form. Although some aspects of engineering require us to keep those complicated load distributions intact, many others, finding the reactions between the wing and fuselage, for instance, can be calculated by using the simplified loads. As the figure shows, we can replace a complicated pressure distribution with a single resultant force acting at a specific location on the wing. The replacement of a complicated load distribution with a simplified one is an exercise in equivalent force systems. In the figures that follow, we'll see structures loaded with two types of loads, forces and moments. You can think of the moments themselves as the equivalent force system of a force couple, no net force but with a resultant moment. Remember this important difference between a force and a moment. We are permitted to slide a force along its line of action, but we are not permitted to displace it, that is, to pick it up and place it on a parallel line of action. We are not permitted to do the latter as it changes the nature of the rotation the force tends to impart to the body. In contrast, moments are free vectors. They have the same influence everywhere on the body, imparting a pure rotational load, and we can move them around at will without changing the nature of how they affect the body. We refer to this ability to slide the force along its line of action as the principle of transmissibility of a force. Suppose we begin with a force acting at point A. We can pick any other point on the force's line of action, for instance B, and apply equal and opposite forces at that point. This is analogous to adding and subtracting the same term to an equation. The net result is zero, so it doesn't have any effect on the result. We can then treat the original force F at A and the force minus F at B as a special kind of force couple. Since the forces are on the same line of action, they produce no net moment, and since they are equal and opposite, they cancel out. The residual force F at B remains, amounting to sliding the original force along its line of action from A to B. We define the resultant force and resultant moment from a set of discrete forces and moments as follows. We will generalize this to distributed forces in Chapter 7. Suppose we are given the body on the left with a number of discrete forces and moments, that is, force couples, applied to it. We want to replace this with a single resultant force and a single resultant moment at point A. The resultant force is just the vector sum of all the forces acting on the body. This may seem contradictory given that we just stated we can't pick forces up off their original lines of action. But the displacement of forces from those original lines of action influences the rotational behavior, and that shows up in the resultant moment. The displacement of forces from those original lines of action does not affect the translational behavior, so they can be combined into a resultant force. The resultant moment is the sum of two sets of terms. The first is the sum of all the moments exerted by the individual forces about point A, and the second term is the sum of all the moments, that is, the force couples. The price of displacing those forces from their original lines of action is a compensating moment, the RAI cross FI term in the resultant moment about A. The second term, the sum of the force couples, does not require any modification, as those loads are free vectors and can be picked up and placed anywhere at will. Let's see if we can attach some intuition to that compensating moment term in the resultant moment by considering the case of a body subjected to a single force F at A, as shown in figure A. For reference, I'll put a dot in the middle of the object to indicate its center. We'll call that G. From our perspective, the force F is to the right of the center, and the right-hand rule would tell us that this force would tend to impart a rotation coming out towards us, for instance, like this. Now suppose we pick a second point B on the other side of the object, as shown in figure B, with the intention of eventually moving our force from A to B. We begin by putting equal and opposite forces at B, just as we did in the previous slide. We intend to use the minus F force at B to cancel the effect of the force at A, but the lines of actions of those forces are now separated by some distance, so we can replace that pair with a couple. Since the couple is a free vector, we can put it anywhere we like, so let's place it at B. Note that the direction of the couple has the same sense as the moment exerted by the force F at A in part A, but it is a larger moment because the distance between the parallel lines of action is larger than the distance between the line of action of F and the center of the object. Now consider what we have in C. The force at B is now on the other side of the center, and by itself would tend to impart a rotation of the opposite sense to what we found in part A. But that's okay because it is more than offset by the moment from the force couple we established in B. This tells us that we are permitted to displace the force from its original line of action as long as we add a compensating moment that offsets the different rotational motion we incur from displacing the force. Finally, we might note that because the force couple is a free vector, we don't have to actually keep it at B. We can move it anywhere we like, including point C as shown at figure D. Two force systems are said to be equivalent if they produce the same resultant force and the same resultant moment about a chosen point of reference. If that chosen point of reference is A, we might just note that these position vectors would be from A to the individual forces. So these would be RAIs. Sets of equivalent forces will induce the same translation and rotation in an unrestrained body. They will also produce the same reactions in a restrained body. In one important area, however, equivalent force systems are not equivalent, and that is in the internal forces they induce within the body. This becomes very important when we make the transition from rigid to deformable bodies, as we will eventually do. Two distinct but equivalent force systems can produce very different peak deflections in a body with finite stiffness. With this caveat aside, we now turn to some examples. Keep in mind that our eventual goal is the reduction of a set of loads, forces and moments, to its simplest possible form. This often involves two steps. First, choosing a point of reference, replace the original set of loads with an equivalent force system at that point of reference. This consists of a single resultant force and a single resultant moment. Then, reducing this resultant pair to its simplest possible form. In many cases, this will involve eliminating the moment altogether by shifting the resultant force to a new location. In the most general three-dimensional case, it involves replacing the resultant force and moment pair with a special force system called a wrench. We will focus on the first step in the first two examples. We will then identify a number of special equivalent force systems before tackling the second step of reducing the system to its simplest possible form. In our first example, we're asked to determine an equivalent force system at point A. This example is two-dimensional and begins with three forces and one moment, that is, a force couple. We want to find the equivalent force system at A. The resultant force is straightforward given that two of the three forces are aligned with the xy coordinate system. We will resolve the 400 Newton force into components along x and y, and then we can say that the resultant F force in x is just 800 newtons minus 400 sine 30, and that gives us a net result of 600 newtons. In Fy, we have two negative contributions. We have a 600 Newton and then plus a 400 cosine 30. And that gives us a net result of minus 946.4 newtons. So our resultant force is 600I minus 946.4 J newtons. So our resultant moment, which is in the K direction, has four contributions. First, the 90 Newton meter moment, which is, again, a force couple. That has the same influence everywhere in the body. So even though that 90 Newton meters is shown at B, it has the same influence at A, and we'll say there's a plus 90 Newton meter contribution from that. And then we have clockwise contributions from all of the forces. So I'll bring the negative out in front. We have an 800 Newton force, which acts through a 100 millimeter or 0.1 meter moment arm. And we have the 600 Newton force, which acts through a 150 millimeter or 0.15 meter moment arm. And then we have the same moment arm for the y component of the 400 Newton force. We add all that together and we get, for the resultant moment, a minus 132 K Newton meter moment, or we could say that the resultant moment is 132 Newton meters in the clockwise direction. In our second example, we also have three forces and one moment, but now it is applied to a three-dimensional problem, and we want to determine the equivalent force system that acts at point E. In a 3D problem, evaluation of moments includes a decision about whether to use a scalar approach or a vector approach. In this case, we have a 40-pound force whose line of action goes through E and therefore contributes no moment. An 80-pound force aligned with the x-axis, whose moment contribution can be easily evaluated with the scalar approach, and a 50-pound force aligned with the z-axis that is a candidate for either the scalar approach or the vector approach. I'll use the vector approach for the 50-pound force. The resultant force in this case is very straightforward since we have three force components each acting in an individual component direction, so we can just write down the result directly. The resultant force is 80I minus 40J minus 50K pounds. For the resultant moment, we have the 700 inch-pound force couple, which is acting in the minus I direction, so that'll be minus 700I. And then the 80-pound force is acting in the x direction, and its moment arm to E is in the y direction, and we can see from the nature of that interaction here crossing r into f, this is going to be in the plus z direction. And so I can say that I've got plus 80 pounds times 8 inches in the k direction. And then finally, so this is in inch pounds, and then I'm going to use the vector approach for the 50-pound force based on this relative position vector from E to C. And so that's, we can see from the figure that that's going to be minus 5I plus 8J inches crossed into minus 50K pounds. So the minus 5 times minus 50 will give us 250, and then we have an I cross K, and the plus 8 times minus 50 will be minus 400 on J cross K inch pounds. Now we'll use the fact that I cross K is minus J and J cross K is I. So the first term and the last term add together, we get a resultant moment that's equal to minus 1100I minus 250J plus 640K inch pounds.